Hey everybody, it's Kevin Wallace, double CCIE and Cisco Press author, and in this video I'm going to simplify multicasting for you, how it works and how to configure it. Stay tuned. What I want to do with you in this video is take the topic of multicast and break it down in a simplified way, still covering a lot of technical detail. We're going to be diving deep into multicast, but I want to present it in such a way that you're going to get a ton of multicast understanding in this one video. Let's get started by taking a look at the benefit of multicast. What is multicast? What are the other options? Why do we want to do multicasting? Well, consider this. Let's say that we've got a video server and I've got 3 PCs, and I use that term PCs generically. You might say, hey, that looks like a Mac. That's not a PC. We've got these 3 different devices on the network, and 2 of these PCs, they want to receive video. And the third one, PC number 3, does not want to receive video. Let's think about different ways of getting the video to the PCs that do want to receive the video. We could use unicast. With unicast, our video server would be sending out a packet to each of those PCs. For every video packet, each PC gets sent its own copy. We send a packet to PC 1, we send a packet to PC 2, and then we go over and over with that again. Well, as you can imagine, that's not going to scale terribly well. It might be fine with 2 PCs, but what if I had 50 PCs that wanted to receive this video stream? Can you imagine the video server having to send out 50 copies of every video packet? That's not terribly efficient. That's going to cause a lot of processor overhead on the video server, and it's going to cause a lot of bandwidth usage on that link to which the video server is connected. Well, let's take a look at another option. Another option is broadcast. Here, the video server saves tons of bandwidth. It saves tons of processing because it only sends each video packet one time. That one packet goes to all of the PCs on the local subnet. Well, that's good in that the 2 PCs that wanted to get the video got it. The video server only had to send each packet one time. But as a downside, PC number 3, it received a video packet and it did not want to receive a video packet. Its network interface card had to take time out of its day to look at that packet and say, that's not for me, I don't want that, and discard it. So what's a better option? Well, you could probably guess based on the title of this video, it's multicast. With multicast, we get the benefit of the video server just sending each packet once, and only the intended recipients get the packet. How can we do that? Well, what we're going to do is have the PCs that want to receive the video, we're going to have them join a multicast group. And a multicast group in the IP version 4 world is going to be a Class D address. We'll talk about IP version 6 a little bit later as well, but in the IP version 4 world, we've got a Class D address. Class D, that's where the first octet is in the range of 224 through 239. Well, here we've got a Class D group of 239.1.1.1, and these 2 PCs have joined that group. So now the video server is going to send out the packet one time, and it only goes to the intended recipients. PC 3 does not have to see it. That's one of the big benefits of multicast. And I mentioned that multicast in the IP version 4 world is going to use a Class D address. Let's talk a bit more about that. Here is the Class D address range, 224.0.0.0 all the way through 239.255.255.255, but there are some reserved addresses in that range I want you to know about. First of all, we've got some link local addresses. And a link local address, and you see the address range here on screen, that address is only usable on the local network segment, only usable on one link. And some of our routing protocols use addresses in this range. For example, OSPF, it uses 224.0.0.5 and 224.0.0.6. RIP version 2, it uses 224.0.0.9. EIGRP, it uses 224.0.0.10. Another class of address that we have is 224.0.1.0 all the way through 238.255.255.255. You'll notice this makes up the vast majority of our Class D address space. These are referred to as globally scoped addresses. They're not limited to a single link, as an example. But within this globally scoped address range, we still have some subsets of ranges that are reserved. Let's take a look at another one of those. We next have the source-specific multicast addresses. These Class D addresses have a 232 in the first octet. Now, what is source-specific multicasting? Well, later in this video, we're going to see that a client that wants to belong to a multicast group can send up a message. We're going to learn that it's the IGMP message that it sends up saying, hey, I want to join this multicast group. And with a specific version of IGMP, IGMP version 3, that device is able to say, not only do I want to belong to this group and receive traffic sent to this group, I only want to receive traffic from specific sources. We can say I want to join a specific multicast group, but I want to receive traffic from this specific server or these specific servers. In the next class of address, our first octet is a 233. These are referred to as GLOP addresses. That's a fun word to say. You might think that GLOP is some sort of an acronym, but really it's not. That's just the name of these addresses. And GLOP addresses can be globally unique multicast addresses that are based on an autonomous system number, like a BGP autonomous system number that a company might have. For example, let's say that we had autonomous system number 65,000, just as an example. In that case, our GLOP address that would be globally unique would be 233.253.232.0 all the way through 233.253.232.255. You see, the second and third octets were determined by our autonomous system number. Here's the way that breaks down in my example. 65,000 in decimal equals FDE8 in hexadecimal. Now, FD, if we look at just those two hexadecimal digits, those two hexadecimal digits in isolation equal 253. Well, that's what we're going to use for our second octet. And E8, if we look at those two in isolation, that equals 232 in decimal. That's the third octet of our GLOP address. And we also have a limited scope address. This is what I oftentimes use in my labs and in my demonstrations because this is a limited scope address. Think of this much like a private IP address, like you use the 10 dot network inside of your network. Maybe you do NAT to get out to the rest of the internet, but inside of your network you might use 10 dot addressing or 172.16 addressing or 192.168 addressing. It's much like that for multicast. Well, that's a look at IP version 4 multicast addressing. Let's now consider IP version 6 multicast addressing. IP version 6 doesn't have the concept of address classes. There is no Class D IP version 6 address. However, it is very easy to recognize an IP version 6 multicast address because it begins with FF. And if our first two hexadecimal digits are both Fs, that means the first 8 binary bits in this 128-bit address, they're going to be all ones. Let's take a look at the example on screen. Let's say that PC1 and PC2, they want to receive this video stream from our video server. They might join a multicast address of FF04::10, and our video server could send traffic that just goes to those two PCs. PC3 does not have to see it. However, beyond those first 8 bits, we also have a flags field and a scope field. Let's consider the flags field first of all. There are 4 bits here. They're called the 0, R, P, and T bits. The 0 bit is called that because it's reserved. It is going to be set to a 0. But the R bit could be set to a 1. And if it is set to a 1, that means the P and the T bits, they also have to be set to a 1. If they are, that would indicate that there is a rendezvous point address embedded in the multicast address. Now, we're going to talk a lot about a rendezvous point a little bit later in this video, but just to give you an idea right now, a rendezvous point is a router that's sort of a relay station. If I want to receive multicast traffic destined for a multicast group, what I could do is tell the rendezvous point that I want to receive that traffic, and it could send it to me. More on that later, but the R, P, and T bits, they're going to indicate whether or not a rendezvous point address is embedded in the multicast address. What about the scope field? What's going on there? Well, we've got several different possible values for our scope, and I'll put them on screen here just as a reference for you. Nothing to really memorize, but you can see that several of these are unassigned. Not all of these scope values have a meaning currently. And some of the scope values would have a particular meaning, such as a scope of a 2. That would be a link local address. We talked about that with IP version 4 multicast addressing. Think of a link local address as an address that is only relevant on a network segment. It's not going to go between subnets. Let me give you a couple of examples. Let's say that we have an IP address, an IP version 6 address of FF02::1. Well, that's a well-known IP version 6 multicast address that references all nodes in this link local scope. The FF tells us, hey, this is a multicast address. The 02 is the scope. It tells us that the scope is link local. It's only valid on this network segment, on this link. and there is an assigned value of 1 at the very end of this address to say that this represents all nodes in this link local scope. Another well-known address is FF02::2. This is all routers in this link local scope. And now that we've talked about addressing and how it differs between IP version 4 and IP version 6, let's take a step back to IP version 4. In fact, when we do some of our demonstrations later, I'm primarily going to focus on IP version 4. Some of the commands are pretty much identical with IP version 6. Instead of saying IP, we would say IPv6, but I'm going to do the demonstrations in IP version 4. And if we're talking about IP version 4, we know that we've got a 32-bit multicast address. But if I'm sending a packet on an Ethernet network, is it enough for me to have this layer 3 address, this multicast IP address? No, we've also got to have a layer 2 address, don't we? That layer 2 address is a MAC address, and interestingly, the multicast MAC address is automatically constructed from our IP version 4 multicast address. Let's go through an example. Let me show you how to do this conversion. Let's say we've got an IP version 4 multicast address of 224.1.10.10, and we want to calculate the corresponding MAC address. Step 1 is to take the last 3 octets and convert those into binary. That's what I've done here. This is the binary representation of the last 3 octets. And if the leftmost bit is not already set to a 0, we should set it to a 0. In this case it is, so we have the same binary string we had back in step 1. Now we want to convert each nibble, as it's called, into a hex value. A nibble is a 4-bit value. Notice how I've put a dot after every 4 binary values. The first nibble would be all zeros. The next nibble is 0001. If we convert that to hex, that's a 1. Well, here I've taken all of those nibbles and converted them into hex values. Now that we've got this hex value, we're going to prepend that hex value with 01005E. That's going to give us our final multicast MAC address of 01005E010A0A. That's the multicast MAC address that corresponds to 224.1.10.10. Let's do one other example. I want to point out something that's very interesting that you should keep in mind. This time, our IP version 4 multicast address is 224.129.10.10. Almost the same address, except in the second octet, we've got a 129 instead of a 1, and we want to calculate the corresponding MAC address. Okay, step 1 was to convert the last 3 octets to binary. Let's do that. And we said in step 2, if the leftmost bit was not already a 0, and it's not in this case, we should make it a 0. Okay, since it's not a 0, the leftmost bit is a 1, we're going to convert it to a 0. That gives us this binary string. Does that look familiar? That's exactly what we had in our previous exercise, which means if we convert each of those nibbles into hex, we're going to get the same hex string. And if we prepend 01005E, you guessed it, we come up with the same multicast MAC address for a different multicast IP version 4 address. That is an issue that we need to keep in mind as we are assigning multicast MAC addresses on a network. It is possible, as we've just demonstrated, to have overlapping multicast MAC addresses. Multicast MAC addresses that correspond to different IP version 4 addresses. And now that we understand a bit more about what multicast is, why is it valuable, we understand a bit about the addressing for IP version 4 and IP version 6, let's see how it actually works on the network. Let's say that I've got a couple of PCs that want to receive multicast traffic, and they're going to be talking to their next top router to say, hey, would you please send me this multicast traffic for this particular multicast group? And the way the PC requests that multicast traffic is using a protocol called IGMP, which stands for the Internet Group Management Protocol. A lot of people think the M stands for multicast, but actually it stands for management. The Internet Group Management Protocol. And we've got different versions of IGMP. Here on screen, the rightmost PC, it's running IGMP version 1, and the one on the left, it's running IGMP version 2. And the router's capable of doing IGMP version 2. Well, here's the difference between those two. My IGMP version 1 receiver is going to send a packet up to the router saying, hey, I want to join 239.1.1.1. And at that point, that router is going to know to send traffic destined for that group out of the interface off of which that receiver is connected. If that router is not yet receiving traffic for that group, then it needs to graft itself on to the multicast distribution tree. It needs to talk to another router in the network saying, hey, can you start sending me traffic for this group? I've got a guy over here that needs it. And with IGMP version 1, there's a timer that's running on that router, a 60-second timer. And after 60 seconds, that router is going to ask the receiver, hey, do you still want to belong to 239.1.1.1? Because maybe that receiver no longer is interested. Maybe it powered off. We're going to request an update every 60 seconds. There's not a proactive way with IGMP version 1 for the receiver to say, all right, I'm out of here. You can stop sending me traffic, but that's a benefit we do get with IGMP version 2. Here, the IGMP version 2 receiver, it's going to send up an IGMP message to our router saying, yes, I also want to join group at 239.1.1.1. And if no other devices connected off of that router interface are members of that multicast group, the router can say, I'm going to start sending that traffic for that group out of this interface. But now, let's say that IGMP version 2 receiver, it's done. It no longer wants to receive this. Maybe it's a video stream. It can proactively tell the router, okay, I'm done. You can stop sending me traffic. I want to leave group 239.1.1.1. That was not possible with IGMP version 1. Only IGMP version 2 could do that. Now, you might be looking at this topology and thinking, okay, what is this, 1995? Is this a bus topology? Is this thick net? Is this thin net? Now, I wanted to show you in theory what's going on with IGMP, but in reality, these PCs, they're going to be connected into an Ethernet switch. Well, here's the question. If I've got an Ethernet switch connected into the router and connected into my receivers, when it receives traffic for 239.1.1.1, how does it know out of which interface it should forward that traffic? Well, what it can do is run something called IGMP snooping. We can do that on our Cisco Catalyst switches. And it's going to eavesdrop in on those IGMP messages. And it's going to see that a receiver wanted to belong to a particular group. And it's going to memorize that information. And when it sees that traffic coming back in destined for that group, it's going to know that the receiver that wanted to receive that, it's off of port maybe gigabit 1/0. So I'm going to forward that traffic out of gigabit 1/0. But I'm not going to forward it out my other ports. So the switch running IGMP snooping, it's constraining how far this multicast traffic gets. Now, here we've demonstrated IGMP version 1 and version 2. There is an IGMP version 3. Let me show you a different topology to illustrate the benefit of this. With IGMP version 3, now by the way, in the real world, you'll probably see IGMP version 2 most widely deployed today, but I want you to know what IGMP version 3 is capable of. Here, the PC is going to send up an IGMP version 3 message to the router, and not only is it saying, I want to receive traffic destined for the group of 239.1.1.1, it can say, but I only want that traffic if it came from a specific source. You see, here we've got a couple of video servers, maybe sending different video streams to the very same Class D address, but they've got different IP addresses, the different video servers. So our IGMP receiver could say, when it sends its message up to the router, we could say, I want to join group 239.1.1.1 and include a source of 10.3.1.1. I want to receive traffic, in other words, just from video server number 2. That's not something we could do with IGMP versions 1 or 2. And one of the interesting characteristics of multicast is the way that initially multicast traffic might flood throughout the network, going out of all router interfaces that are configured for multicast. We're going to talk a little bit later in this video about exactly how that happens and how we can prevent that from happening. But initially, this multicast sender might be sending traffic to the receiver, and it goes into R1, and R1 says, well, I've got a couple of exit interfaces. They're both enabled for multicast, and it sends the traffic out of both of its interfaces, going to R2 and R3, which each send a packet to R4. That means the receiver, it's getting a couple of packets. It's getting a duplicate copy of the packet. Now, what's going to prevent that from happening is something called RPF, reverse path forwarding. We don't want to receive duplicate copies, so here's what R4 is going to do. R4 is going to say, all right, I'm getting in some traffic, and it's coming from 10.1.1.1, and I'm receiving this traffic coming into gigabit 0/0 and into gigabit 0/1. Here's the question I want to ask. If I were to send traffic back to 10.1.1.1, according to my unicast IP routing table, which egress interface would I use? We check our IP routing table and we see that to get to network 10.1.1.0, our egress interface would be gigabit 0/0. Well, based on that, router R4 says, okay, if I receive traffic from this multicast sender, I'm only going to accept it if it came in to interface gigabit 0/0. If the traffic comes in gigabit 0/1, I'm going to drop it. We're going to discard that packet. That's reverse path forwarding, and the benefit of that is the receiver is not receiving duplicate copies of a packet. And the next huge concept we have to wrap our brains around as we're talking about multicast is the concept of a distribution tree. When a multicast sender is sending out multicast packets, those packets are going to travel over branches of a tree, if you will. And there's a couple of different types of trees we can have. There's a source distribution tree and a shared distribution tree. And based on these trees, we have a couple of different versions of something called PIM, PIM. That's Protocol Independent Multicast. Protocol independent means that it does not matter what our underlying IP routing protocol is, this PIM can ride on top of that. It doesn't matter if we're using a RIP or OSPF or EIGRP, we're independent of that unicast IP routing protocol. Think of PIM as a multicast IP routing protocol. And with a source distribution tree, this sender in the upper left-hand corner of your screen comes up on the network, and it's going to be sending to a destination Class D address of 225.1.2.3. And with a source distribution tree, if we're running a PIM Dense Mode, here's what happens. Router R1 is going to get that packet, and it's going to flood it out of all of its other interfaces. R2 and R3 get it, they flood it out of their interfaces. Did you see what happened there? R3 flooded the packet up to R2, R2 flooded the packet to R3, which then flooded the packet out to the receiver. The receiver got 2 copies of the same packet. Let's watch that again. Here's what happens with a source distribution tree. We go into R1, it sends it out of its egress interfaces into R3 and R2. They send it to one another. The receiver, it got 2 copies of that packet. Well, here's what's going to happen with PIM Dense Mode. R2 is going to look around and say, I don't have any interfaces that have received any sort of a join request. I don't have any clients that have sent me an IGMP message saying that they want to belong to this multicast distribution tree. I really don't think I need to receive this multicast traffic. And R3 that received a multicast packet from R2, it's going to say, you do not need to send me any more multicast traffic. I'm already getting a copy of that from R1. That's my optimal path back to the source. And R2 received a copy from R3, and since R2 no longer wants to receive multicast traffic, it's going to send a prune message. Just like we might take some pruning shears and literally cut a branch off of a tree, we're going to prune off router R2 from this distribution tree. We're going to send a prune message to R1 and R3, and router R3, it no longer wants to receive multicast traffic from router R2, so it's going to send it a prune message. And as a result, we're left with an optimal tree. The traffic goes from the server to router R1, which goes directly down to R3, which then goes out to our receiver. Now, what if we had another receiver that comes on the network? Here comes another receiver. Router R2 just received an IGMP message saying that somebody connected off of one of its interfaces wants to receive traffic for 225.1.2.3, and it's no longer a member of the tree. What does it do? Well, it's going to graft itself back on. We send a graft message up to R1 saying, can I be part of the tree again? And that will be acknowledged, and now R1 is going to send traffic both to R2 and to R3, and they send it out to their attached receivers. That's PIM Dense Mode. But one of the drawbacks of that is that initially we flooded multicast traffic throughout our entire topology. Well, this was a smaller topology, so we could better visualize it, but think if we had dozens of routers. And when a multicast source starts streaming, that initial traffic gets flooded throughout the network. That's called a flood and prune behavior. That could impact network performance. And in some implementations of PIM Dense Mode, that flooding and pruning happens about every 3 minutes. That can dramatically impact network performance on a larger network. However, some of the more recent implementations of PIM Dense Mode have a feature called state refresh, so we don't have to do that flooding and pruning every 3 minutes. But still, it's considered a best practice to use PIM Sparse Mode as opposed to PIM Dense Mode. Sparse Mode uses a shared distribution tree. Remember earlier we talked about the concept of a rendezvous point? Well, here, router R2 is acting as that rendezvous point. And if my receiver wants to join the group of 225.1.2.3, it's going to send its IGMP message up to router R3, and router R3 has knowledge of a rendezvous point in the network. This is going to prevent that flooding and pruning behavior. The multicast source comes up and it can send just to router R2. Anybody that wants to receive that traffic, it can go request that traffic from router R2. So the receiver, it sends up an IGMP report message. And then router R3, it's going to send a join message up to router R2. Now, notice the way this is written. *, G. The star represents the source. We're saying we don't really care where we get it from. We don't care what the source IP address is, but the group we want to join is 225.1.2.3. That's the G in star comma G. So now the multicast source is going to send traffic to the rendezvous point, which is going to relay it down to R3, which then sends it out to the receiver. Well, that's great that we avoided that flood and prune behavior. However, we've got a downside here. That was not an optimal path to go from R1 to R2 to R3. It would have been much better if we just went from R1 directly down to R3, and R3 knows that. R3 saw the source IP address of that multicast sender, and it looked at its IP routing table, and it determined that a more optimal path would have been the path from R1. So what R3 is going to do, it's going to send an S, G join up to R1. The S is the source, because it now knows the source IP address of the sender. It's going to say, I want to receive traffic from this source destined for this group. And then R1 is going to start sending it traffic directly down to R3. However, notice the traffic also went to R2 to R3 to the receiver. The receiver got 2 copies of the packet. We no longer need that traffic from R2, so R3 sends a prune message up to R2, and now we've got an optimal path. We're going from R1 to R3 to the receiver. Beautiful. That is called shortest path tree switchover. When we make that switchover from the rendezvous point to the shortest path tree, the most optimal path. So we ended up with an optimal path, and we did not have to do flooding and pruning, which could be really negative on a large network. That's the reason we say that PIM Sparse Mode is preferred over PIM Dense Mode. And now that we've talked a lot about the theory of multicast, let's go out to a live interface and let's do some multicast configuration. I want to show you how we set up PIM Dense Mode, first of all. Then we'll set up PIM Sparse Mode, where we go to each of the routers and we tell the routers, hey, here is the IP address of the rendezvous point. And then I want to show you a trick to make things a little bit easier for us. We don't have to go to all of the routers in a network and say, here's the IP address of the rendezvous point, here's the IP address of the rendezvous point. It would be much better, much more efficient, much more resilient if rendezvous points could advertise their availability to the network. That's a feature called Auto RP. I want to show you how to set that up. But let's get started out of the live interface by setting up a basic PIM Dense Mode configuration. Let's begin our multicast configuration on router R1. We're going to go into global configuration mode, and we need to enable multicast routing on this router. To do that, for IP version 4, that's what we're going to be doing in this demonstration, I'm going to say IP multicast-routing. If I were setting this up for IP version 6, it would be IPv6 multicast routing, but again, we're going to do an IP version 4 demonstration. Now I need to go into each of my interfaces that I want to participate in multicasting and enable them for multicasting. And I'm going to do that by specifying the PIM mode. Remember, we talked about dense mode and sparse mode? First, let's set this up for dense mode. I'm going to go into interface fast Ethernet 0/0, and we'll say IP PIM Dense -mode. Let's do that for interface fast Ethernet 0/1 as well, IP PIM Dense Mode, and let's do it for interface fast Ethernet 2/0. We'll say IP PIM Dense Mode. And we've configured router R1 for IP PIM Dense Mode operation. Let's go to router R2, and we'll do a similar configuration. I'll say IP multicast-routing, and I'll go into interface fast Ethernet 0/0, and I'll say IP PIM Dense Mode. Let's do that for interface fast Ethernet 0/1 as well. And let's move on to router R3. In global configuration mode, again, we'll say IP multicast-routing, and we'll go into interface fast Ethernet 0/0, and I'll say IP PIM Dense-mode. We'll do that for fast Ethernet 0/1 and for interface fast Ethernet 2/0. IP PIM Dense Mode. And we've now configured multicast routing on all of these routers. Well, routers R1, R2, and R3. The multicast source that you see on screen, I'm actually going to be using a router for that. And the receiver, I'm going to be using a router for that as well. And before I start sending multicast traffic in the network, here on router R3, let's give a show command. Let's say show IP-M route. Instead of looking at the unicast IP routing table, we're looking at the multicast IP routing table. And right now, we don't have any entries except for this one that gets entered automatically. This is used for auto RP, we could automatically learn the IP address of a rendezvous point, and I'll demonstrate that for you in just a bit. Now let's set up some multicast traffic. I'm going to go to my multicast source, and let's start a ping. I'm going to ping with a destination address of a multicast address. I'm going to do a ping to 239.1.1.1, and I will repeat it a lot of times. I'll say 999999999. That's going to send a lot of pings. Great. Now, let's go set up the receiver to receive those pings. We'll go to the receiver and say, I want to join the group 239.1.1.1. Here's how I can do that. Let's go into interface fast Ethernet 0/0, and I'll say IP IGMP join-group 239.1.1.1. This is going to cause this router, acting as a PC, to send an IGMP join message up to router R3 saying, hey, I want to receive traffic destined for 239.1.1.1. And I'm curious what our multicast IP routing table looks like now. Let's go back to R3, and let's once again do a show IP mroute. Oh, look at this. We now have what's called an S, G entry. Now, by the way, for every S, G entry, there's a corresponding star, G entry. The star meaning any source associated with this group, but we know of a specific source. We're getting the multicast traffic sourced from 10.1.1.10. So this is an S, G entry. That's the source. That's the group. We can also look at this output and determine what is the ingress interface for the multicast traffic. It's coming into what interface? Well, we can see the incoming interface for this S, G entry is fast Ethernet 0/0. That's coming in from router R1. We can also see our outgoing interface or interfaces. We've just got one. This is called the OIL, the outgoing interface list. We see that we're going out of fast Ethernet 2/0. And finally, notice the flags on this S, G entry. Just notice for now that we do not have the J flag set. The J flag says that we have joined the shortest path tree. We are using the shortest path tree, but because we're using dense mode, we started out with the shortest path tree. We didn't have to join it. So there's no J entry here. That's going to be different. That's the reason I'm pointing it out now. It's going to be different when we set up PIM Sparse Mode. In fact, let's do that now. Let's set up PIM Sparse Mode. Let's go back and revisit router R1. And remember, PIM Sparse Mode is going to use a rendezvous point. Let's make router R2 our rendezvous point. And one way for routers to know about that rendezvous point is to statically configure the rendezvous point. Let's do that. On router R1, I'll say IP PIM RP-address. And again, if I were doing this with IP version 6, it would be IPv6 PIM RP-address. IP PIM RP address 2.2.2.2. I'm using the loopback interface of router R2 because a loopback interface doesn't go down based on changing network conditions. Now let's go into each of our other interfaces on R1 and say that we want to run PIM Sparse Mode. I'll say interface fast Ethernet 0/0 IP PIM Sparse Mode. Let's do it again for fast Ethernet 0/1 IP PIM Sparse Mode and interface fast Ethernet 2/0 IP PIM Sparse Mode. Great. Now let's go to router R2. This is going to be our rendezvous point. And I'm going to say IP PIM RP address is 2.2.2.2. Let's go into loopback 0 and say we want to run IP PIM Sparse Mode. Let's go into interface fast Ethernet 0/0 and say the same thing. And finally for interface fast Ethernet 0/1. Now let's set up router R3. I'll say that my rendezvous point is 2.2.2.2. Let's go into fast Ethernet 0/0 and I'll say IP PIM Sparse Mode. Let's do it again for fast Ethernet 0/1. And finally for interface fast Ethernet 2/0 IP PIM Sparse Mode. Now let's check our multicast state here on router R3. Once again, I'll do a show IP mroute, and you'll notice that this looks really similar to what we had with PIM Dense Mode. However, notice that this S, G entry that we have right here, it does have the J flag set. We did not have the J flag set earlier. The J means that we have joined the shortest path tree. We did SPT switchover, in other words. Remember how that worked? We stopped receiving traffic from the rendezvous point and we started receiving traffic via the optimal path. That was the SPT join, and we see that that has happened here. So without the flooding and pruning behavior, we're getting traffic via an optimal path. In fact, let's go back to router R2, our rendezvous point, for a second. Let's take a look at its multicast IP routing table. Let's do a show IP mroute here, and notice this S,G entry. We're receiving traffic from the multicast sender, but because we've done shortest path tree switchover, we're no longer sending it to anyone. For a very brief moment, we were sending it down to R3, and then it did SPT switchover, and we can see that we're not sending it to anybody else because look at the oil. The outgoing interface list is null. We're not sending it to anyone, but we are receiving traffic coming in from router R1 via Fast Ethernet 0/0. And in this example, we saw how to tell the routers in a topology who was the RP. However, there's an easier way, especially if we have a large topology. We can have the rendezvous point announce itself as the RP. There are a couple of processes that work here. We need to have an RP and we need to have a mapping agent. A mapping agent listens to group 224.0.1.39. It's listening for any router announcing itself as an RP. And the mapping agent then resolves any conflicts that might exist among these routers that want to be RPs. And this mapping agent announces the multicast group RP mapping to the group of 224.0.1.40. You see this entry? It was appearing in all of our routers as soon as we enabled multicast routing. We're going to be announcing to this multicast group that the rendezvous point for the group of 239.1.1.1, the rendezvous point is 2.2.2.2. Now in our case, router R2, it's going to act as both the mapping agent and the RP. So we need to go to each router and remove the information about the RP. Also, we need to change our PIM mode from sparse mode to sparse dense mode. The reason is we've got a bit of a paradox here. You see, our routers need to use multicast to identify the RP. However, how can we listen into this group if we're not running multicast? We cannot run PIM Sparse Mode until we know the RP, and we cannot learn the RP until we listen into this group. Well, what if we could do this? What if we could run dense mode just long enough to listen into this group and learn the address of the rendezvous point? Then we could switch over to sparse mode. That's an option. We could run sparse dense mode, which says run in sparse mode if you can, run in dense mode if you cannot. So we're going to use dense mode to learn the identity of the RP, then we'll switch over to sparse mode. Let's go to each of our routers, remove the rendezvous point configuration, and change the PIM mode for each interface. Then we'll configure auto RP. Let's start on router R1. Let's say that we want to get rid of our statically configured PIM RP address. I'll say no IP PIM RP address 2.2.2.2. And let's go into interface Fast Ethernet 0/0, and let's say that our PIM mode is sparse dense mode. Same thing for Fast Ethernet 0/1, sparse dense mode, and for Fast Ethernet 2/0, sparse dense mode. Now let's go to router R2, and in global configuration mode, we'll say no IP PIM RP address 2.2.2.2. We'll go into interface Fast Ethernet 0/0, and we'll say IP PIM sparse dense mode. Same thing for Fast Ethernet 0/1. And same thing for our loopback interface. Finally, we go to router R3 and do the same thing. No IP PIM RP address 2.2.2.2. Let's go into interface Fast Ethernet 0/0 and say IP PIM sparse dense mode. Fast Ethernet 0/1, IP PIM sparse dense mode. Fast Ethernet 2/0, IP PIM sparse dense mode. And now that we've set everybody up to learn the RP automatically, we need to go to router R2 and configure it to automatically announce its availability as an RP. And we also need to configure it as a mapping agent. Let's go to router R2 and we'll say IP PIM send RP announce. Now we're going to be announcing that our loopback 0 interface is the RP. It's 2.2.2.2. How far do I want to advertise this across how many router hops? Well, we can set a time to live value here. We can say that the scope is 16, meaning that I'm going to be setting my advertisement time to live value to 16. Remember that the time to live, the TTL value, gets decremented every router hop, and once it reaches 0, it's discarded. So I'm going to be able to span several routers with my advertisement saying, hey, I'm the RP. And we want our mapping agent to be able to hear that information. And I misspelled announce. Let's fix that. That's better. Let's now configure the mapping agent by saying IP PIM send RP discovery. Again, I'll set the scope to 16. So router R2 is now going to be listening for anybody advertising itself as the RP, and it's going to be able to resolve any conflicts and then advertise that information out to 224.0.1.40. And we've also said that R2 is willing to be an RP. It's advertising its availability, and it's using loopback 0 as the RP address. Now that we've done that, let's go over to router R3 and see what multicast groups we know about. Let's do another show IP mroute. And we've got several entries here. Notice that we now have an S,G entry for 2.2.2.2, 224.0.1.39. Let me give this command one more time. And notice we've got this additional S,G entry, 10.1.4.2 for this well-known group of 224.0.1.40. What we're saying here is we're learning information from 10.1.4.2. We're learning from our mapping agent, in other words, about an RP. And that RP that we learned from this group is 2.2.2.2. We can get further confirmation about who is the RP by doing a show IP PIM RP command. And it tells us very clearly that for group 239.1.1.1, we're using a rendezvous point of 2.2.2.2. And this also tells us that we're running PIM version 2. And speaking of PIM version 2, I'm not going to take time to configure it because it's so similar to Auto RP, but I want you to be aware that there is an alternative to using Auto RP. Specifically, if all the routers are running PIM version 2, you can configure something called BSR. That's an abbreviation for Bootstrap Router. Now, with BSR, you configure BSR candidates. That's similar to the RP announce configuration that we gave on router R2. And you can also configure BSRs. Those are similar to mapping agents. That's going to work very similar to Auto RP. Cisco came out with the Auto RP solution before the standards bodies came out with BSR, but they work basically the same. All right, that is your look at multicast. We started with the basics, saying, why do we need multicast? Why is it better than broadcast or unicast in some situations? We talked about the addressing with IP version 4. With IP version 6. We saw how to take an IP version 4 multicast IP address and convert that into a corresponding multicast MAC address. We saw how the RPF check worked. We talked about IGMP versions 1 and 2 and 3. We contrasted PIM Dense Mode with PIM Sparse Mode. Then we came out to a live interface and we saw how to configure PIM Dense Mode. Then we saw a couple of ways of how to configure PIM Sparse Mode. One, where we go to each of the routers and we say, here is the IP address of your rendezvous point. And finally, we just took a look at a way that that rendezvous point information could be advertised using Auto RP. If you want to learn even more about Cisco routing and switching technologies, just click the link in the description or on the right side of the screen, and I'll send you more training videos. And also, if you don't want to miss any of my YouTube videos, be sure and subscribe. Thanks for watching, and I'll see you next time.